14.1 graph sine, cosine, and tangent functions. So I'm going to put all right, so I'm going to do sine first. So the increments that go on here, it starts at 2, or we go all the way out to 2 pi, which you'll see why in a little bit, but basically these increments here are the increments that are on the axis of your unit circle, okay? And then we do the same thing in the negative direction. It goes out to minus 2 pi. So it's pi over 2, pi, 3 pi over 2, 2 pi. And then we go up to 1, and it's negative 1. All right, so normally what happens is I just show you what it looks like, but I don't really explain it, but I do want to explain it because the other day when I explained it in pre-cal, they said, oh, that makes so much more sense, and I think that they kind of understood where it was going. So if I asked you what the sine of 0 is, you would tell me that it's what? Like, think of the unit circle. So the sine of 0 degrees is what? 0. So we put a point there. What about at pi over 2? Or 90 degrees?
1.
So it's 1. Okay, remember these are all axis points. So then of pi would be what? Sine of pi. 0. How about sine of 3 pi over 2?
Negative 1.
-1. And then of 2 pi? 0. Okay, so what you're going to notice is it follows this pattern, okay, and it's going to keep going. Every time you get to the next thing, it's going to be the next position, okay, and then we could do it going backwards. The sine of negative pi over 2, okay, that's the same as 3 pi over 2, so it's down here. Minus pi, well, it's the same thing as pi, it's 0. Negative 3 pi over 2, that's the same as pi over 2, so it's 1. And then of negative 2 pi, well, it's the same as 2 pi, which is 0. And then we just connect the dots. Now, it's rounded, okay, not like, don't do this. You know, it doesn't look like that. Okay, it's rounded, so we always go a little bit beyond so that we show that it keeps going. It doesn't just stop after 2 pi. We just stop because we don't need to graph anymore after that. And it doesn't have to be perfect. It's pretty hard to connect the dots like perfectly when you're not supposed to like, you know, make them like pointed and stuff like that. But that's the parent function for sine. So we graph from negative 2 pi to 2 pi, and it goes from negative 1 to 1. So the way I remember it is sine always starts at 0, okay? And then you just always follow the pattern. It's up, down, down, up, up. You get it just keeps following that. Cosine's going to be the same pattern, but for its value. So it's actually going to end up being like shifted a little bit. So any questions about sine before I do cosine? Okay. So then cosine. And again, I'm going to draw out my increments. we go -1 to 1 again. All right, so what is the cosine of 1? Or, sorry, cosine of 0.
1.
Yeah, it's 1. Okay, so sine started at 0, cosine starts at 1. How about cosine of pi over 2?
0.
Cosine of pi?
-1.
Yep. Cosine of 3 pi over 2?
0.
And of 2 pi?
1.
Yep. And so then going backwards, we just work our way back. So it was up, so we go down again, and then back up. And then we just connect. Now with this one, you always want to start down here and round it up because that's the next point is going down that way. So if you look at the two graphs for sine and cosine, they are the same, they're other than just being shifted over, technically. So they follow the same pattern for how it works. It's just, like I said, shifted. So I always think cosine looks a little bit more like a W just because of how it, on its parent function. Any questions about cosine? Anything? All right. We're on to tangent next. So tangent is going to work well, it's not going to look anything like that, but the setup of the points is the same. So you'll still set up a -2 pi to 2 pi and, well, -1 to 1, but we don't really care about that much, so. All right, now what do we know about, like, let's say the tangent of pi over 2? What is that?
Undefined.
It's undefined, okay? So that means if I were to plot a point and I were to say the tangent of pi over 2, well, it's undefined, so there's nothing there, okay? So when that happens, we have what we call an asymptote, okay? And I'll write out what that word in just a second. But basically what that means is we have a graph, and it can't cross it. It means no matter how close it gets, it'll get really, really close, but it'll never actually touch it, okay? Now, that concept is probably, like, really confusing right now. You're probably like, well, how can I keep getting closer and closer and never touch it? But that's like, in my philosophy class, my professor was going to go open the door, and he said, it doesn't matter how close I get, I'm never actually touching the door handle. And I was like, he goes, I'm constantly getting closer to it, but I'm never actually touching it. And I was like, okay. Didn't really understand the concept, but you just kind of have to trust me that graph can't cross it, so we just draw it basically touching without actually touching. So what happens is we put a dotted line at pi over 2. And then the same thing kind of happens at 3 pi over 2, right? It's also undefined there. So I put a dotted line there. And so then at minus pi over 2, they have the same thing. And then at minus 3 pi over 2. So tangent is going to have an asymptote at all the pi over 2 values. So the dot, dot, dot represents an asymptote. Don't cross them. And And all that means, like we said, is that it's undefined and it doesn't exist there. So tangent graphs are kind of fun, actually, because kind of just like a curly line. So what is the tangent of 0?
0.
It's 0. So we put a point there. And then, what about at pi? 0. Negative pi is also 0. I could keep going out. Okay, every increment of pi or 2 pi is going to have a point there. So then what happens is we get really, really close to the asymptote. We come up, never actually crosses it. It just gets really close and looks like that. And we do that at all the points. So we'd have another one here. And it doesn't have to be perfect. It just needs to show that it's curving. And same thing with minus pi. And so it would just keep going like that. And so basically it goes on to infinity in both in the y direction, but in the x direction, it's stopped on either side by the undefined values where our asymptotes are. Now, these, because of the direction that they're going, they are technically called vertical asymptotes, which I'll get to that in a second when we start talking about characteristics of tangent, but just so you know, they're vertical. Later in math, you'll learn that there's also horizontal and oblique ones as well, but we don't really get those. We briefly will hit them probably before we're done with this school year, but they really show up in pre-cal and calculus is where we really get into using them. All right, so I'm going to do some stuff about sine and cosine. So I'm going to do it specifically in regards to the amplitude and period of sine and cosine, and then we'll do it completely separate for tangent. So the amplitude and period of the graphs of y equals a sine of bx and y equals a cosine of bx, where a and b are non-zero real numbers, are, so the amplitude is equal to the absolute value of a. So the amplitude's always going to be positive, which is why it's in the absolute value bars. A negative sign in front, much like when we already graphed parabolas, right? Okay. Much like when we did that, the negative sign in front would just mean that the whole graph was being reflected. So that's why we put the absolute value in there. And the period is 2 pi over the absolute value of b. So again, we just take the number that's in front of x, if there is one. Okay, otherwise we assume it's 1. And so we put that in there. So for our parent function of just y equals sine of x, okay, what we graphed at the top, our amplitude is just 1, which is why we did negative 1 to 1. Okay, amplitude is the distance from the 0 on the y-axis, okay. And then the period, we went out to 2 pi because the number in front of x was just 1, so it's 2 pi over 1, which is just 2 pi. So that's how you would find it, and that's how you restructure your graph if you were going to actually be graphing them. But my requirement with this section is that you know how to graph the 3 parent functions that I've given you, and then that you can tell me the amplitude and period, and then for tangent where the asymptotes occur, just mathematically. And that's it. Okay, so the section's not as scary as it might kind of sound. All right, so let's look at tangent, and then we'll get into a few examples. So some characteristics of y equals a tangent of bx. So with tangent, it doesn't have an amplitude, so we're going to be talking about the period and vertical asymptotes. And vertical asymptotes, a lot of times I will write as VA just for short to not have to write out the whole thing every time. Of the graph of y equals a tangent of bx, where a and b are non-zero real numbers, are, and so the period, it's a slightly different formula than before. It is pi over the absolute value of b. So it's different in that it's not 2 pi, it's just pi. And then the vertical asymptotes are at odd multiples of pi over 2b, with b being the absolute value again. So pi over 2 absolute value of b. So that's like if you had, like, say it ended up being pi over 4, it would be at 1 pi over 4, 3 pi over 4, 5 pi over 4. Okay, that's what it means by odd multiples. It's like the odd number on the top. All right, so like I said, I modified the instructions for this section just because of the nature of it. So it says to graph. We don't do that. We just find the, that was nice. Find the amplitude, period, and I'm just going to put vertical asymptotes, and then I'm just going to say if applicable for all of these so I don't have to write it twice. Obviously, only tangents have vertical asymptotes, and only sine and cosine have amplitude. So just whatever is applicable to the given situation is what you're finding. So with number 6, we have the sine of 1 over 5 x. Okay, so amplitude and period are applicable for sine. So my amplitude is going to be equal to what? Amplitude is the number that comes where?
Before the sine.
Yeah, before sine, so it's a sine bx. So amplitude is a, which is what in this case?
0. 1.
1. If it's not written, it's a 1. If it was 0, there would be no function there at all. All right, and then the period is 2 pi over the absolute value of b. So it's 2 pi over the absolute value of 1/5. And you don't have to write the absolute value bars if it's already positive. It's just if it was negative, you need to write it. So I'm dividing by a fraction, meaning I do what? By what?
Keep.
Yeah, keep, change, flip. So I'd be multiplying that by 5, so that ends up being 10 pi. So my amplitude is 1, and my period is 10 pi. So all that means is where we had, like, say for this one, if you were going to graph it, where we originally had 2 pi in our parent graph, it would become, so I'm just going to go up here and I can just point it out. This would become 10 pi. Okay? Then this would become 5 pi because it's half of that, and then we would split the other numbers in half. So it'd be like 2.5 pi and 7.5 pi would be our new values there that are going on there. That's why I say the graphs look the same every time. So I'd rather you know what they are changed to. You would be able to graph them, no problem, once you know that, basically. Let's see. 10. F of x is equal to 2 over 3 sine of x. So amplitude would be what? Yep, 2/3. And period would be what?
1 pi over 2 pi.
Okay, 2 pi over 1, which is 2 pi. Okay, and you don't have to write the over 1, but I just do it so that if you go to look back, you know why. Okay, so the 1 came from, there was just a 1 in front of x. Amplitude is the number in front of sine. Or cosine, as the case would be. Let's see. Let's look at a cosine one. 12. Y equals pi over 4 cosine of x. Amplitude. Pi over 4. And period.
2 pi.
2 pi over 1, which is just 2 pi. Alright, so I don't really know why they split it like this, but they pretty much, in the first section, they just do sine and cosine. Then they go down a little bit. They skip like 2 or 3 problems, and then they come back to graph the function, literally the same instructions. And I don't really think the problems get harder, so I'm not really sure why they do it. But anyways, so number 16, y equals 2 sine of 8x. So my amplitude is 2, and my period is what?
Pi over 4.
Okay, so 2 pi over 8. And then that will reduce. If it can be reduced, I do want you to reduce it. So that would be pi over 4. But always leave it in increments of pi if that happens. Let's see. 18. Y equals 3 cosine of pi x. So amplitude. And period.
2.
Yeah, so 2 pi over pi. So that's the exception to when you can reduce. Obviously, I just said to leave it in terms of pi, but the pi's cancel, so obviously we're going to do that. I just mean don't, like, take your calculator out and be like, well, 2 times pi divided by 7 is blah, blah, blah. Just leave it if that happens. All right. And then I do want to look at a couple tangent ones here. So number 20, we have f of x is equal to 2 tangent of 4x. So a tangent, remember we're not looking at amplitude, we're looking at period and vertical asymptotes. So the period for tangent is what?
Pi over 4.
Okay, so pi over the absolute value of b, so yes, pi over 4. And then vertical asymptotes.
Pi over 8.
Okay, so pi over 2 times 4, which is pi over 8. Okay, so again, if we were actually doing it, it would be occurring at pi over 8, 3 pi over 8, 5 pi over 8, and so on and so forth. Okay, it's the odd multiples of it. But you don't have to write that every time. I just wanted you to have it for reference. All you have to write is that it's there. And then last one, number 22. f of x is equal to 4 tangent of pi x. So period would be what? Okay, pi over pi, which is 1. And then vertical asymptotes would be where?
Pi over 2.
Nope.
One half.
Okay, so it's pi over 2 pi, which reduces to 1/2. So I don't mind if you just go through and you just tell me the vertical asymptote is 1/2. But if you don't write this first part of how you got there and it's wrong, all your credit's gone. Okay, because there was no work to show me what you did. So I don't mind if you're really confident that that's what you did. But again, with all the, and I'm just saying that because with all the wrong answers that were just there, I would have no idea how you got that. And so I'm taking off all the points. Versus if you show me that you set this up and you just reduced wrong, I'm like, okay, they just reduced wrong. That's only like a point off instead of like 5 points off, for example. So
is it always pi on top? Like, is that what the odd multiples mean, or like could it be different?
yeah, so it's always the only thing. So I'm just going to, or well, here, let me just go back here because you can't even see that. So odd multiples of pi over 2 absolute value of b. So the only thing that's being changed is b. So the only thing that's changing is the number that's in front of x in tangent.
Okay, so it'll be like always pi on top.
Mm-hmm.
Okay.
Yeah, and the only, now with this one, obviously, what happened was it was pi over 2, and then b was pi, so it reduced.
Okay.
So the pi wasn't there at the end, but it was to begin with.
Okay. That makes
So yeah. Any questions about those? So today that's what we're doing. I'll give you a couple problems just so that you have something to work through. But then tomorrow we're going to add what happens if it gets shifted left, right, up, down, or reflected. Okay, meaning we'll be doing it the same thing. It's not like I didn't make you graph these easy ones and then tomorrow I'm going to be like, oh, you have to graph them all. Like, I'm not going to do that. So for this section, 11, 13, 17, 19, and 21.